opportunity to present our work. The project that we worked on is an emerging algorithm that uses activation information for large language models. And this is a joint work with Akash, who's sitting here. I should hide this so okay. Anyways, there are like two other names down there which you cannot see, which is like Faiz and Navid, our PIs at MIT. A little bit about us. Amin is a fifth-year PhD student, PhD candidate at MIT. Almost there. I guess he's graduating soon. He's in Meki department. I'm a second-year PhD. I'm in MIT IDSS, which is the abbreviation for Data Systems and Society, and I'm part of LEADS. My research journey starts in like EE and math, so very technical. And at the beginning, I was doing info theory because I love math, and it kind of made sense. But then I realized that the problems are not timely anymore. They're like more important problems to solve at this point. So I moved to this like ML era, and then I did some stuff in practical distributed machine learning, how to do gradient compression and these kind of things. But then I realized that I want to do theory. I want to use the math that I learned. So right now, what I do, I pick the problems that are in like reliable private machine learning, efficient machine learning, but I try to tackle them using mathematically grounded solutions. At least I try to do it. It's hard to do these kind of things in LLMs, but I do my best. All right, now I hand it over to Amin to introduce himself and goes over the background.
Yeah, thank you. So my background, very different. I really more dabble on the practical side. Coming from a mechanical engineering background, a lot of the things that I do usually involve, in some form, actually building stuff and doing things in the mechanical world. A few examples of things I've done throughout my 5 years at MIT: building linkage mechanisms that can trace really weird shapes, like MIT, designing airplane models, optimizing shapes for different loading conditions, topology optimization, that bridge you're seeing there. And all of this was being done in the context of generative modeling. So really the goal at the Decode Lab and what we do is really take a lot of the lessons learned from AI and try to implement them in a way that makes sense for mechanical engineers and to build real physical products. But this may not be very inspiring as far as LLMs go, because this is the talk that we are giving today. But as LLMs developed over the years, I really got into it specifically when it came to creating CAD models. So we have this example here where we actually used an LLM to create collaboratively a design for a turbine blade. So here I'm just going over this, coming up with design ideas. We can go back and forth with these LLMs, and then at the end, I can formulate exactly what design I want. And these kinds of models can actually create CAD for me. And this is kind of where I got more into LLMs, and this is the story of me getting involved with LLMs. So this is just an example of me describing exactly how I want to design my turbine blade, and we'll see that this model is actually capable of producing 3D geometry that's accurate to this kind of specifications. Can maybe skip a little bit forward here. Basically, it leads to a 3D CAD, which you can take to a CAD software and work with it. So this is kind of how I got into LLMs in the beginning. Just a little bit of backstory. But I really want to go over some of the history of LLMs, and it's always good to look back at how things developed. If we look at the progression of language modeling and LLMs, start with the early days, you have your n-grams, your Markov models, and maybe some early neural networks. And this is way past when I was even involved in any of these things in academia. But a lot of that led to the research that we have today. And then we get sort of the machine learning world comes in 2012 and 2013, you have word-to-vec, and then sequence-to-sequence models. These are usually like RNNs at the time and LSTMs. But then in 2017, you have the attention is all you need paper, which gives you the transformer architecture. And going from there, it just keeps blowing up. So you get your BERT and GPT models coming out in 2018. And this is the time I'm still in undergrad. I'm not even done yet. with my undergrad, and this stuff is just happening. In 2019, you get GPT, and this is when I'm just finishing my undergrad. And then going through it in 2020, you get larger models that do encoder only, decoder only stuff becomes more prevalent, and then you get to the GPT world, and all these different models kind of blow up. So we see that going from very simple language models to the world of LLMs today, you get instruction following, you get multimodality, which is really what's important to someone like me. Because when I'm doing CAD or I'm generating designs, that really makes a big difference for me. So this is kind of where I get even more interested in this kind of model. And then, we have today's models with reasoning, agentic AI, and broader commercial integration. And currently, there seems to be a lot of focus on this kind of efficiency, inference time scaling, and the cost of actually running these models. So it's a really big deal because we're getting wide adoption. I think a recent story that broke the news in Twitter was this thing where the CEO of Shopify was saying everybody needs to explain why they can't use AI for whatever tasks, which is kind of signaling where this wide adoption of LLMs is just going to happen, and this is inevitable. And it does really matter how we deal with these models. The efficiency and the cost of this plays a big role in the future of AI and how people will perceive it. So I want to really go back to the basics and take a look at how we train LLMs. So how do we come by these models right now? The more, I guess, up-to-date way of thinking about it is, it used to be two steps that people thought of, was pre-training and fine-tuning, but these days you get the reasoning, reinforcement learning, RLHF that comes into play as well. So really, it's become more of a three-step kind of approach. But the typical way you train an LLM, you start with pre-training. So this is training your LLMs on a huge corpus of text that is just gathered from everywhere. And then once you have that base model, you adapt it using fine-tuning to do, for example, instruction following or perform some specific tasks that you're interested in. And then more recently, we see human feedback come into play with RLHF, and reasoning becomes a big deal with, again, reinforcement learning enables that with GRPO. And we can talk about all of these, but what I really want to highlight here is that when it comes to the training cost, the majority is still going to be on the pre-training side. So this pre-training costs the most computationally, as well as in terms of time and investment. So this is, I think, a key pillar of how we developed our method, and I think it's very important to put this into context early on. This is essentially what we're going to fall back on as one of the principles in our method. So what this leads to, naturally, is it's much cheaper to do fine-tuning. So you can take a base model that is released in an open source environment, and you're going to have people fine-tune it on many different tasks. It could be math, code, instruction following, reasoning, whatever it is. This is just the natural way of things happening in the open source world. But even in the professional environment with AI companies developing larger models, this is often the case where, examples of this is not that far in terms of the open source world. This is just an example of Llama 370B and how many different fine-tuned versions of this are just openly available on Hugging Face. Just the instruction tuned itself has been fine-tuned 43 times, and so many other fine-tunes from the base model exist. So really, it's just a huge space of these different checkpoints. But again, even in the professional world, we see kind of this issue where a lot of times we all make mistakes, or sometimes things change the training process. So a lot of these companies may start with a pre-trained base model and do some training on this, maybe partially stop it, or something fails in the training, or data is changed, or for whatever reason, the checkpoints are abandoned. So because of this nature that fine-tuning is cheaper, you're going to end up with in a setting where there's a lot of checkpoints that are going to go unused. And this is normal because people experiment a lot on this. But naturally, we can think of, well, where's this leading us? So we have all these checkpoints. Naturally, what do we think of? Do we just throw it out? What do we do? And efficiency is in the forefront of current AI landscape. there's all these headlines of DeepSeek breaking the market, cutting NVIDIA's evaluation in half, and doing this. So really, it does matter that we don't waste resources, energy, both from an environmental perspective and from a cost perspective. And this can create a big problem in the world if we are not careful with this. So naturally, what we think of is this wasted compute, or can we actually use this in a reasonable way? Also, in the open source world, can we do better with no additional cost? A lot of people are spending energy and time and money developing these checkpoints from the same base model. Can we actually do something better with these? And so this is where naturally model merging emerges. So the idea with model merging is you have a bunch of expert checkpoints, and these models have been trained on different tasks, let's say. And this graphic, I have intentionally made it this way because I really want to highlight one thing. That is that usually when we look at these different checkpoints, what we look at are weights. We just look at the model's weights, it could be billions of parameters, whatever these parameters are. And typically with merging,
You should do something about that. Yeah.
Yeah, if you just click on hide, it goes away.
You should go out of the share. And could you hide the panel as well? Like
Yeah.
so that-
Yeah, absolutely.
yeah, so
yeah.
I think if you're sharing the screen, you should go to the yeah, there you go.
nice. Yeah, so as I was saying, these expert models are usually looked at from the perspective of the weights. So typically what most existing merging methods are doing are, well, they take different experts and they somehow find a way to put all these weights together into one final model. The thing that's really cool about this is that your final model is the same size as any of those individual checkpoints. So what you have is essentially a model that operates at the same efficiency as any individual checkpoint. Now, you can think of an alternative way of doing this as, let's say I have my math expert, I have my code expert, I have my reasoning model, or whatever expert that it is I have. And every time I have a math question, I go to my math expert. Or if I need something to do with graphic design, I go to the graphic design expert. This can be very costly in terms of memory, especially because you have to hold on to all these checkpoints and run them separately. But the ideal world and the ideal case for merging is you basically take all these checkpoints, somehow find a way to put them together into this one model that basically takes expertise from each of these and allows you to kind of strike a balance between all these different expertise at the same cost as running any individual model. And that's really, I think, the key thing that merging tries to do. And again, the note I'm trying to make with this graphic is that most models are looking at weights. But do we only have weights to look at, or can we do better than just weights? So if we just looked at the weights of a model, is that really enough or not? So what we thought of was we can get inspired by a lot of the works that we see in model compression. A lot of times, these approaches look at the activation space. And what do I mean by the activation space? When you're running an LLM, what you do is each layer takes something as input, performs some operation on it, and gives you an output. Those inputs and outputs at each layer represent what the intermediate activations are. And the space of these activations actually turns out to have very rich information about the model. And this is not coming from a hunch. Maybe initially it was a hunch, but when we looked into it in model compression, this is actually widely adopted. So one example of this is activation-aware quantization. So this is a very famous and widely used quantization method that you may have heard of. And if you go on Hugging Face, a lot of models just have the AWQ version. And what this activation-aware quantization does is looks at the activation space. And in fact, what they show is that they can get a significant improvement over normal quantization. And here, the example GPTQ does is it does a quantization and then post-training. So they quantize and then fine-tune again the quantized model to get even better performance. And yet, without fine-tuning, looking at the activations enables you to outperform them. So this is kind of giving us an idea of how powerful this activation space can be. And model compression is really a good medium for us because when you think about it, when you're doing merging, you're kind of trying to compress each model and somehow bring them together in a smaller package. But this is not the only case. So it's not just quantization that can benefit from activation space information. It's also in sparsification and pruning these models. So you can get rid of a lot of parameters in the pruning context. And this was also widely cited in the adopted paper. The method specifically they use here is called Wanda. This was out of Meta. What they did also was they performed pruning on large language models using the activation function. Exactly how they do it is not going to be that important. Kaveh will cover exactly how this is done. But what I really want to highlight is that when you look at weights only, the performance that you get after pruning these models, it is significantly worse. And it's not just like a small difference. Just to highlight an example, in the 7B, the first column, you can see that when you just look at the magnitude, which is just look at the weights, you have a perplexity of 46, and then you go to 54 by just looking at the activation space. This is no training, so there's no additional cost associated with this other than just simple inference. And the sparse GPT example in this table is doing post pruning training. So after pruning, they do additional training. So you can see that even without training, the activation space has such rich information that you can just skip the training part and still get the same results. So this is basically a very strong signal for us to use activation space information when it comes to merging. So we can see that activation really matters and it encompasses a lot of vital information about the underlying model. So the question is, how do we extract this activation space information? And this really matters a lot. So the typical way that the existing literature does it, and we also adopt the same, is to use some calibration corpus. So you have a bunch of text that is representative of the data that these LLMs have been trained on. You give it to the LLM and you record those intermediate activations. And this essentially will give you a way to represent that activation space. Now, a good question that we often get here is, what is this calibration corpus? How big should it be? Does the quality matter? And this is very important when it comes to training, because when we fine-tune, the quality of the fine-tuning data is critical to the outcome of the model. But what we see in current literature, and our observations as well, is that when you're just trying to look at the activation space and represent it, there is much, much less sensitivity to the calibration set. So in AWQ, what they look at is how much calibration data they need to get a certain amount of performance. And then they compare this to GPTQ, which does post quantization fine-tuning. So you can see when you fine-tune, you need a lot of data to get even close to that performance that you get just looking at the activation space. So what this graph is telling us is you need far fewer data and far less sensitive, you're far less sensitive to the actual data itself as long as it's representative when you're trying to extract activation space information. So this is also shown in this paper when they switch between two different calibration data sets. So I think this is a very key observation, that when you're looking at the activation space, you're not as sensitive to the quality of the data as you would be if you were doing fine-tuning. So this is a very important thing. Same thing gets observed in Wanda. When they're doing pruning, again, you see that huge gap between the post-fine-tuning method and just using activation spaces. So this is a key observation that we have. The activation space is not as sensitive to calibration data as training. And this really allows us to leverage this much more practically when it comes to merging, and Kaveh will cover exactly how that happens. So, quick recap. We saw that pre-training is the majority of the work and the cost. So we think the pre-training plays a big role. But beyond the cost, it's also a very important foundational point. So in the R1 technical report, they really highlight the fact that post-training is very powerful, but it is very important to also have a good pre-trained model. So the pre-trained model really builds all the foundational knowledge and everything that you need to actually be able to, get better performance down the line, whether it's through fine-tuning, inference time scaling, or anything else. So this is one of the key points that we want to keep in mind when we're developing our merging methods, that the pre-training matters a lot. And that really determines the quality of the downline performance. And the other one is activation space matters. So this one we just covered now. We saw this in AWQ, we saw this in Wanda, and we can see that all of this kind of plays a big role in how well you can leverage the activation information to improve your models. Now I'm going to hand it off to Kaveh to cover exactly how we took these two principles and came up with our method.
You also merge pre-trained models then, or fine-tunes of the same pre-trained model?
Right, so I think Kaveh will cover exactly how the merging specifically works, but just to quickly give you an overview, the base model, the pre-trained model, plays a huge role in how merging is done.
Okay.
Because what you do is you measure how each fine-tuning evolves from that base model. So that the differential is what you look at.
Back to your question, we merge fine-tuned models from the same pre-trained model.
Yeah.
And so in order to explain our algorithm, I first need to tell you how people do merging. They're doing merging before us. The core concept is this delta pipeline. They have the pre-trained model, it's kind of small here, but theta pre shows the pre-trained model parameter. And then you have different fine-tuned models, so you can calculate the delta that you need to take to get to that fine-tuned models. And then, the general framework that most of the previous researcher follows is to somehow transform these deltas in the weight space. So they use weight space information to transform the delta, and then they combine the delta and they apply it on theta pre. For instance, simple example is simple averaging. This is the first work on LLM merging, which basically tells you to average the models out, which you can see if you just take the deltas and sum them up, you're gonna end up here. Then there's an extension to this, which is task arithmetic, which tells you instead of just taking the sum of deltas, have this hyperparameter lambda, which controls how much you wanna move in that direction. So it's a very simple extension. And then there is drop and rescale merging method, which transforms the delta by pruning and rescaling them and then summing them up. So the takeaway from this slide is that all of them follow the delta pipeline. Take the deltas, do something on top, somehow combined. There are two other methods, ties, merging, and widen. They also follow the same pipeline, but the transformation and the part that they combine them is a bit more complex. Looking at this, when we were going over the literature, we realized that they only use the weight space activation, and they are not using the weight space information, and they are not using activations at all. And then the question that we were asking ourselves is that how can we use activations for merging? Because we observed that in the compression literature that's very useful, and also we realized that the pre-trained model is very important. So we should try to maintain the capabilities of the pre-trained model as much as we can. So a very simplistic view of machine learning models is that you have an input vector, your activation, and you have a weight matrix, and you multiply this together and you get the output. So y is equal to xw. And then in the merging setup, we want to go from w to w plus some delta w, which is the amount that you want to move. And then the output change, basically the output error, as I'm gonna elaborate a bit later, is x times this delta w. Why this output change is important? Because if you take x to be your activations based on your calibration corpus, and delta w to be the delta that you wanna take, then this output change kind of signals how much you're gonna lose the base model performance on the calibration corpus. So if your calibration corpus is representative of the pre-trained data, you want to keep this as small as possible. And then if you follow the color code in the slides, you can see that there is this natural mapping between activations and weight space. So if activation is large, the corresponding weights, the rows, are more important, and we should try to change them as small as possible. And if the activation is small, it means that the pre-trained model do not rely on that weights that much. So we're free to move in that direction. So what we did, we tried to incorporate this intuition into the merging algorithms and come up with a complementary solution that you can apply on top of previous merging algorithms. So what we did is like use activations. Based on these activations, calculate the importance mapping, the salient mapping, take the delta from your favorite merging method, and then just multiply this together. So what we do, we have theta aim is like theta of pre-trained model times the importance, like 1 minus the importance mapping times the delta that we want to take. So if weight is important according to activations, we try to don't move that weight as much. And if the activation is small, the 1 minus activation would be 1, and we move in that direction.
It's just the activation or the error?
So this is the activations. Let me go back to this slide. This is, sorry. So it's x times delta w. This is the quantity that we try to make it as small as possible.
Yes.
So as you see here, the term that we have with a minus sign here is minus activations times delta merge. So we try to kind of put that in the algorithm.
I see.
Like the way to see this is that if the activation is 1, activation importance is 1, we normalize the importances. You don't move that weight at all. And if the activation is 0, you're allowed to move in the direction that the merging algorithm is like proposed.
I see.
So we sketch the delta based on the activation. And that's why it's a complementary solution. You can take your favorite merging algorithm and just apply this on top. All you need is a calibration corpus, calculating the activations and multiplying them together. So it's computationally efficient as well. You just need to do one pass over the calibration set, keep the activations, and then you can apply it on top of whatever merging algorithm you want.
I see.
High-level view of our algorithm is that we have pre-trained model, fine-tuned models, and we have like bunch of merging algorithms that give us the delta merge. What we do is the line below. We take the calibration corpus, calculate the activations, and take that delta and calculate the new check. For instance, like one corner case, one interesting question here is that, okay, what if I just take one fine-tuned model and apply this like activation informed merging on top? So you have one fine-tuned model, one pre-trained model, and you want to kind of update the delta. We observe that if you do this on QM models, you get a better check. So this works even when you have one fine-tuned model. So like there is a lot of like interesting stuff happening in activation space, but that's not our work. That was just more like a question to look at. Anyways, so in the next slide, I'm gonna show you what happens.
Can I just quickly ask a question on that last point? When you say it works better, which benchmark is specifically?
Yeah, so we just looked at same benchmarks that we run for the popular.
We have like 6 benchmarks.
And again, change slight change.
Right,
Yeah, like
right.
it's not a
No, I think I get the point. That there's some regression even when you fine tune it.
But it's even better than the task that you're fine tuning for. Like if you fine tune for instruction following.
I think the general instruction following.
I mean,
Yeah,
the
Just
delta
but
is
if you
small.
fine tune for coding, and then you merge
No, but that's a
the
different
fine-tune
case,
base.
right? Because like I think what they're saying is that's why I asked benchmark. Right?
Yeah, exactly.
The benchmark is like say OpenLLM.
Yeah.
Technically, after fine tuning,
You should
you
use
always
this.
improve. What you're saying is, if you calibrate it again, that on those benchmark, you see a better performance.
Yeah. But
It's
yeah,
very,
I agree
very
with that. But
tiny.
if it is anyway,
Yeah.
that's not.
It's a very tiny delta, but it's a positive delta.
Yeah.
But again, that's not the main point of my argument. Just an interesting point. All right, so as I said, this is a complementary solution. You can apply it on top of whatever merging algorithm that you have, and we did. So in this plot, this is like on MBPP, which is a coding benchmark. So on the left side, the orange bars, it's like the base model, the code model, the instruct model, and the math model, the models that we're merging. This is Llama 2, if I'm not mistaken. And then we tried different merging setups. So merging 2 out of these 3, all 3 together. So the first one is instruction, code, and math, the ICM, and then the rest follows the same. And then for all,
What is the calibration corpus? Like, is it like general corpus or like you do task specific?
it's a general corpus that the only thing that matters is that it should be representative of the pre-trained data. So we use this data set called Pi, which we follow like this. We basically use the same data set as previous works, AWQ and Lambda, and they use Pi, which is part of their pre-trained data. All right, so again, they like each of these four is like different merging setups, and for different merging algorithms like DTA, DT, these like different merging algorithms. I'm not gonna get into it. But the point that I wanna convey is that the blue ones are the merging algorithms themselves, and then the green ones is when we apply AIM on top of them. So as you can see, you almost always improve when you go from the blue one to the green one. When you apply AIM on top, when you use activation, it doesn't matter what's the method that you're using. It doesn't matter the merging setup. It's always helpful, at least in the setup that we tried. We observed the same thing for mathematical questions as well. So this is a math data set. You can observe the same thing. The merging setup is similar. The benchmark is math. It's same for instruction following. I just chose like math and code as two examples to show. A very interesting way that you can see this is that we start from a pre-trained model. Then people fine-tune this model and try to make it better on different benchmarks. They kind of push the Pareto frontier. So we start with like the star, which is the pre-trained model, and we fine-tune it. So we got to the dark blue line. So we push the Pareto optimal for different benchmarks. And then people apply this merging algorithm. So they further push the Pareto frontier line. They get to the green dashed line. And then the interesting question that we were asking ourselves is that, okay, how AIM changes this Pareto frontier? And as you can see in these benchmarks, when you apply AIM on top of merging algorithms, you can further push the Pareto frontier, which is very interesting. I think the right way to kind of measure the effectiveness of merging algorithms is that how much you can push the Pareto frontier, because if we have a model that is good at math, we have a model good at coding, we wish to have a model that is at least somewhat better than the naive merging of these two. That's why this plot is very interesting to me. If you're not convinced that it works, this is the table that we have all the results there. You cannot probably read the results, but so many green numbers, which is the delta between the merge algorithm and when we apply AIM on top of the merge algorithm. You can check this in the paper if you want. Well, as Akash said, this is not how exactly we came up with this idea and how it happened. The real story is that we were taking a natural language processing course, and we were looking for a course project. And we asked Akash about interesting problems. He told us merging is an important question. So we went on Hugging Face. We found these are different fine-tune checkpoints for Llama 3.28b. So you can see the names of them and then how they perform on different benchmarks. And then the question that we had was can we merge all of this together and get a better model? Are we there yet? And if you look at this table, you can see that we have very good checkpoints like NVIDIA Open Math that does very well on math. And we have very bad checkpoints like that B Adam, the second one from the bottom, that basically is pure garbage. So as you can imagine, you cannot just merge these together. And when you use this merging algorithm, prior merging algorithms to merge these checkpoints together, the performance that you get is worse than the worst model, worse than the worst check. So it's a complete failure. So math OpenAI task arithmetic reaches 0.2%, which is worse than the worst. So it's a complete failure here. So the answer to that question is no.
Okay.
But
For now.
Okay.
I mean, it's still no for us too. This is a very hard task to answer.
Yeah.
But then we were okay, maybe this is such a hard question to ask. Let's ask an easier question. Let's remove the bad checkpoints.
Yeah,
And
that was the question.
yes, and see if you can merge like good quality checkpoints. So if I go back to this one, the one that we chose was NVIDIA Open Math, which does very well on math. Llama IP Instruct, the one in the middle, and Instruct a special SQL. So these three were like doing good enough. So we're like, okay, this is a fair question to ask. So we merged them and we filtered out the low quality models, and still the performance is not there. So that activation and very relaxation is the previous name for our method. I didn't update the plot. But as you can see, so in this plot, what I want you to see, like there are like three dashed lines. The most left one is the worst model, the second one is the base model, and the rightmost one is the best model on that benchmark. So in most cases, the merge model performs worse than the base model. So again, merging is not working in this scenario, in my opinion. And that's how we like, started the whole thing, that it was like, maybe dead space is not enough. And we should do something else to at least, so basically this plot was what was inspiring for us to use the activations to maintain the capabilities of the base model, because we're like, okay, at least I expect to have the same performance as the base model. All right. Final recap. We are in the fine-tuning paradigm. Like we should kind of adjust our algorithms to that. Merging is a technique that allows many experts to work together. Activation space is important. People showed that for merging. We kind of took the first step to show it for, people showed that for compression. We took the first step to show it for merging. And we developed AIM, which is a complementary solution to prior merging methods. And most of the times improves them. It pushes the Pareto frontier as well. And what we want to do later is to further explore how to incorporate this activation. So the way that we are like incorporating it right now is like one of the easiest way that you can do it. Probably you can like think about like more complicated ways to do it, more mathematically grounded ways to do it. And then the other like future direction that I find very interesting is to look at the activations of fine-tuned models. The only activation space information that we are looking right now is the pre-trained model. We just look at that one. So if we figure out this one, then we can think about how can we like incorporate activations of fine-tuned models. And the QR code over there would take you to the paper. Thanks a lot for giving us the opportunity to present our work.
That's awesome. I have a question on the previous slide. So in the math, the third plot.
Yeah.
I mean, it does seem like the first method, which is the old method that you have, sort of goes past the dotted line. I thought you said that it doesn't. None of the merging methods currently can get past the best model.
Yes. I mean, that's true. So what we observed in this scenario was that, if we merge NVIDIA Open Math, which to our knowledge was the best checkpoint for math
At the time.
For that specific architecture.
For that specific architecture. With like Llama Instruct and this like Instruct Spatial SQL, we can get a better performance on math with our merging strategy, which was really interesting to us. I don't have the plot right now, but we kind of managed to recover the Pareto optimal frontier, but like by kind of trying different parameters for our algorithm. But yes, that was one of the interesting observations that we had earlier. I wish I had the plot too.
How does it? So let's say if you were to take a bunch of math models together, and merge those. What happens then? Do you have any intuition? Like, if this like...
Yeah, I would fall back on this one here. What you see is when you're merging math with code or math with instruction tune, you get better performance than the math alone. So whatever your math fine-tune model was doing on the benchmark, the merge model does better than that by quite a distance. So this is it's the same observation we had with the open math thing. When you merge it with even a model that's not even a math fine-tuned model, you go beyond even what that model was capable of to begin with. And this was, a little surprising, but as I came to find, like, a lot of the prior merging methods, I also observed that, where the Pareto front is not, so your fine-tuned model on math is not your necessarily even itself a Pareto optimal model. So once you merge, you may push the Pareto front slightly above that as well. So not only do you take that math expert and get it to be better at general knowledge, but somehow it also improves its math knowledge on the way there. So these are all interesting.
So here's another top of that, right? I think you guys alluded to mixture of experts before. If I were to take, what's your intuition on this? If I were to take, say, Mixtral, right, and just literally take all of their experts and merge them. One thing which is kind of interesting there, the architecturally they're all the same, right? And the reason I'm asking this is because like increasingly the new models that are coming out are like huge mixture of experts.
Yes.
Right? Is there like any intuition there? Because I think the other neat thing is that you have a little bit more information because there's a router on the activation directly. I wonder if you have any thoughts about it.
I mean, it's an interesting question because like one of the, like we were trying to look for models that have different experts to merge, and one of the ideas was, okay, there's these mixture of experts, maybe we can just take one expert at a time and see how that plays out. To be honest, I can't make a definitive statement about that because it's just hard to know. But if we were to kind of extrapolate from this, which is usually not a good idea to extrapolate, especially because like we're such a early stage, in my opinion, at least in LLMs, it's not a mature field. But if we were to extrapolate, I would imagine there is a world where you could maybe merge these mixtures based on the router's information to get a more compressed model. But would that be as performant as the mixture of expert? Probably not. But maybe you can strike a balance. So it's better than not having it's better than having one expert from the beginning on your training. But is it as good as all of them together? Probably not.
The reason I asked that question is because I think you also we mentioned pruning. And I was trying to understand like what does pruning look like on a mixture of experts? Because you could just prune out experts by merging them. Typically, you get rid of weights, which feels almost like why would you lose things if you could merge them? That's kind of why the question came. That maybe if you find that in the mixture of experts, two experts are almost identical or like differ really by a very tiny amount. Does it make sense to combine them using the
During
activation?
inferences.
Yeah.
Yeah,
Or even
that's-
like even
that's
during
definitely
training, if a penalty like this.
Yeah.
Like the new Lava 4 model has like 16 experts.
Yeah.
Like, do we actually need 16 experts?
For sure.
Or if there at least there's redundancy. I guess I think that's the question. If there's a redundancy that you expect, like something really being too close and more sort of like your aim method. Because the first part of your work is like, let me assess. Looking at the activations, how far are these things? Right? It's like,
It's definitely interesting.
because that would be very, very valuable.
Yeah, even I think if you could do better than the router during the inference somehow, I think that would be kind of interesting. It is a good question.
But one thing is how to come up with a fair comparison with mixture of experts, because like they have like 16 models loaded at the same time and they have a router, and if we merge we're gonna have a single model. So how should we?
Oh, I wasn't even thinking. I think it's a very good point. I wasn't even thinking like merge them to one model. I was just trying to understand, as I think what Shiv was saying, if there's 16 or like in these like bigger models, 200 experts, chances are there's like a lot of redundancy. Right? So not merging to recover one model, but even if you can reduce the expert number by 10% or 20%, that's like, in terms of running the same model, that's a huge improvement. Even if you drop the performance by 1 or 2%, I mean, do you know what I mean? Like, because your memory footprint just goes down. Right? You don't have to load those models.
You can use like a couple of GPUs instead of 30.
5,000, yeah.
That's a really good point.
For the calibration data, have you tried using both data from the pre-trained model and the
So I think, so really what I try to highlight there with this, yeah, so like here, really switching between, so this is not, so when they're doing AWQ, it doesn't matter if it's the base model or it's the instruction tuning or whatever. They do the quantization on whatever model, they use the same calibration corpus.
Hmm.
Even though that calibration corpus is more representative of the pre-trained. What they show is that, what I was trying to get across here is the sensitivity of just, if you're just interested in looking at the activation space, it is not going to be as big a deal in terms of like how high quality or how big your calibration corpus is. This is what they observed. And so this is actually quite nice because it gives you, a way that is, first of all, low cost. Second of all, it's kind of not going to be that hard to generalize to different experts. So that's kind of like why the future direction is very promising and looking at other activation spaces as well. But yeah, so unlike fine tuning and training, you're not so sensitive to that data.
Yeah, but as a counter argument, if you use the same number of samples from maybe one of the tasks that you find you know, then it wouldn't work, right? Like
Probably, yeah. I would say, yeah, if you have a very, very limited distribution.
Yeah.
So yeah.
Yeah.
So if you're trying to be adversarial with your like calibration corpus, you can definitely find an adversarial calibration corpus. But again, like if it's a general corpus like this,
yeah.
what they observed in both cases, whether it's pruning or quantization, was that the activation space representation, you can kind of grab that from more or less any representative data.
Yeah, I have a follow-up question with Nikhil's question. So,
You want to speak a little bit louder?
yeah, okay. So, have you thought about like just completely getting rid of this calibration data? So, my intuition is the reason the result, let's say quantization or for the merging, they're less sensitive to the size of calibration data is because of the structure of the model. Let's say the weight matrices, they might have like their singular value being uneven distributed.
Yeah.
So, and actually that's what people in continual learning, that's what they do, right? If you want to inject new knowledge into your model, look at their eigenvalue.
Oh, yes.
That's where the, yeah.
Do you think that is it?
All right, so that's a very good question. So at the very last slide, the recap, I had this like, future work direction that, let's use more grounded.
Yeah.
Anyways, I'm tired. Thank you. So that's a very good question. So the alternative approach that we tried and we observed that it gives us a similar performance is exactly what you said. So in the continual learning literature, people look at the gradients and the sensitivity of the output to the inputs, and they kind of try to move in the directions that doesn't change the output much for the base model, and learn new things. It's like orthogonal gradient descent and these kind of things. And so we looked into that one. We came up with another method. We tried it and we got the similar result. So that's it was almost exactly identical. And then I tried to kind of justify that these two methods are the same, and they are actually the same if you take the Taylor expansion of the formulation that you get from the gradients and the continual learning and whatever. This would be the first order approximation to that. I can tell you more like with more mathematical notions, but yes, you can do that, and yes, you get a similar result.
And on the singular value, we did look at like can we compress each expert and look at their singular values and see if we can use those specific things for merging. Okay. Disclaimer.
Let's revisit this in the so the reason Nikhil is asking this question and I was asking this question is because they did manage to get two different things around quantizing KV cache and in his case continual learning to work. The challenge was around identifying the directions that you should constrain.
Yeah.
And it turns out that they had to spend a lot of time to figure out what are those directions.
Yeah.
Because typical metrics that they initially were going through, they don't seem to actually give you a good idea.
Yeah, so that's what we observed.
Yeah.
We went to the singular value decomposition. We got very, very bad performance.
Yeah.
But that's just probably because it's very naive the way we did it, so we didn't really put in enough.
But when we use the calibration data to find those directions, we got the
No, this is the reason why I think
Yeah.
we were saying that to maybe let's revisit this because that was the challenge, and I think you solved it by using everything. But and Nick will probably can expand on this. What they ended up with.
Yeah, so Krishna found a paper called Adaptive Singular Value Decomposition. Basically, what they do is add SVD. Yeah, okay. But what they look at is the similarity.
No. There was another paper.
Yeah, like they take a calculated data too, and then they look at the similarity between the input and the output activations. And if the similarity is very high, like for an example, an identity matrix would have like maximum similarity, which means that the transformation is not happening in a subspace. It's using the entire rank of the matrix, right?
Yeah, makes sense.
And if the similarity is low, that means probably the matrix has a lower effective rank, which means you can like throw away those
Oh, yeah. Well, that's interesting.
activations.
So one of the things we thought of was, what if, because like right now, this first order approximation just looks at the input activations. One of the things we were like, okay, well, how about the mapping between the input and the output? Maybe that's more rich information. So yes.
Our first attempt to use eigenvalues or like singular values failed. Like we tried to apply SVD on weight matrices, kind of say that okay, we can prune the base model weights and then move in the orthogonal direction. That failed completely. The output was 0. Like, I'm not exaggerating. Yeah.
No, I think that there's also this, like, because these models are so deep, there's error accumulation, so we can quickly just destroy the whole thing at some point.
No, I think it'd be good to maybe like can you share like your paper? It'd be helpful to like survive. Okay. Let's see if there's any other questions.
Did you guys like look at scaling laws for this at all?
So, no, not really.
No. What do you mean exactly by scaling laws?
Well, I guess this is kind of touched on like by the mixture of experts as well, but like how much compression works or like how different the calibration data can be from whatever you're trying to measure.
We are going to look at calibration data size and how that changes our performance in the next revision of the paper, but we haven't right now.
They can't expect to see the same plot as AWQ, that the size of the activation is not. That's our expectation.
I also believe that there's no dependency. All right. Let's thank the speakers again. That was a wonderful presentation.
Someone has raised.
Oh, Aditi raised the hand. Okay.
Just to make it more accessible for myself, from a use case perspective, from a usability standpoint, does this tie with the Instruct Lab strategy? Like we do small language model fine tuning. So if we have fine tuning model for task A and a small language model fine tune for task B, so can we use this model merging for like providing to the users that this is going to enhance your model utility further?
I can add some context to the Instruct Lab mention here. So we have you guys are aware of Instruct Lab. It's a way to customize language models. Again, this question is, can we take multiple different models that people have, say, customized for their use cases and have this tool merge them to get a model that does fairly well across. So it's the same model, customized on 3 tasks, let's say. Right? And can we merge them to get a better performance? Or maintain
these results you could.
Yeah.
So like if we look at the results that we got in our 2 sets of experiments, yes, the answer would be yes. But I do feel there is an open question in merging in general.
Yeah.
not just in our method, but existing all these merging methods is what happens when you have a lot of checkpoints? Because like
Yeah.
all of these papers, including ours, it's like 3 experts or 2 experts. What happens when you have 50 experts?
So the reason I really like this question is kind of like also to count that one of the reasons why I said this is a very interesting problem to work on is it helps us address this problem. I do also agree with you in this particular case, the method should really work because it's the same exact model that has been progressively trained.
That should work.
So you're finding that every time you merge back to the original model, you gain it's positive, it's not negative. I think that's the point that this question touches on. That just Aditi, I think one of the plans at least we've had is to bring this in into the toolkit to prevent any kind of regression.
I think our inspiration was continual learning essentially. So that's kind of the idea.
One thing that I can add for that context, like is the future work that we have in mind, is to use the same intuition